So maybe you have done the 1D infinite square well, but what if it has a bump in there? How do you find the stationary states, the solutions that don't depend on time in that case, which are very important for other stuff, and so I want to go over this, and there's more than one way to do this, but I'm going to use Python. So let's just set up the problem here. And I'm making this for myself because I forget how to do these things. So this is for me. And if you like it, that's great. Okay, let me move this a little bit. So here's my well. It's not an infinite square well. It's an infinite square well with a bump. And I just put a bump in there just so it could be different. But anytime you have some non-standard potential, we can use the same method to solve it. And we're gonna use the finite difference method and turn this into an eigenvalue problem. That's our goal. So let's just jump back and think about where we're coming from. I'm gonna go through this super fast because that's not really the point here. Here's the one-dimensional Schrödinger equation. Now, it depends on both time and space, but I can write the wave function as a product of a space part and a time part. And if the potential does not depend on time, then I can easily solve for, I get the equation as one side that depends on time, one side that depends on space, and the only way that that can be true is if they're both sides are equal to a constant. We call that constant E, and then I can solve for the time part, and I get that from my time part. E to the negative I t over h bar. Got it. Okay. And then I'm left with the space part. So now I have to solve this space part. It only depends on space. There's no time dependency in there. And there's no imaginary numbers either, which is kind of nice. But you might have an imaginary wave function later, but we'll deal with that later. Okay. So we're going to use the finite difference method. So in the finite difference method, we're going to take our space and break it into finite pieces. So it might look something like this. Here are 7 wave functions. I'm going to break this into 7 spots from, no, 6, I'm sorry, 1 to 6. I started at 1. I should have started at 0. That was my fault, but whatever. So instead of having a continuous wave function, we're going to have a discrete wave function. So it only has values at certain points. And you can imagine it could be any shape or whatever, it doesn't matter. If I do that, if I have a discrete wave function like this, I can redetermine the first and second derivative in terms of these finite differences. So let's just look at 3 of these points. The ith point right there in the middle. If I want to take the derivative at the ith point, I could do that by looking at the difference between the one before it, I minus 1, and I'll show you an example, and then the next one, I plus 1. And so the derivative is just the slope between those points, which would have a displacement of 2 delta x. Okay, so I can write that derivative, the partial derivative at the ith element, as I plus 1 minus I minus psi I minus 1 over 2 delta x. It's just a slope. Okay. Now, what if I want to find the second derivative? Well, the second derivative would be the derivative. I can do the derivative at the halfway point right here and the derivative of the halfway point right there, and it's the derivative of the derivative, right? So I can take the difference in slopes from the half point right there and the half point right there. So this is psi prime is the derivative right here, psi prime I plus 1/2, I'm sorry, it's right here, minus psi prime I minus 1 is the derivative right there. And then I have to divide by just 1, I'm going 1 delta x from there to there. And if I write that out, it looks like this, because now I have my derivative at the half point is just right here is going to be psi I minus psi I minus 1. This one's going to be psi I plus 1 minus psi I. So this is my psi prime at I plus 1/2. And this is psi prime at I minus 1/2. And so it's just the difference between those. And then I need to divide by delta x. So you see I get 2 delta x's here. Now if I just bring the other delta x to the bottom, I get delta x squared. And then this term I have I plus 1 minus I, and then minus I, and then plus I minus 1, right? Because I have a minus here. So I get this right here. And that's kind of a big deal. This is how we write the second derivative as a finite difference. So if I want to find the second derivative at psi I need the one before it, the next one, I plus 1, and the one before it, I minus 1. And I need that space interval. Okay. let's go back to the Schrödinger equation. So here is the Schrödinger equation. I have a second derivative. I want to write that second derivative as a finite difference. So I'm going to replace that second derivative with the finite difference, and it looks like this. So here I have the negative h bar squared over 2m. I can factor out the delta x squared, and I put that down here. And then this term right there is just, that's my leftover part. That's that second derivative. And now over here, I still have psi I. I have psi. That's the ith psi, right? And v, the potential, there's a potential at every point too. So I have vi. And then I have that constant e, and then I have psi I. Now, it turns out that I want to group those psi i's together. So I'm going to combine this v psi I with this negative 2 psi I with all that stuff over there. So this psi I plus 1 gets that term. Psi I minus 1 gets that term too. And then the psi I gets this term, which has the vi in there. Should that be minus? Let's see. That's minus plus. No, I think it's right. Okay. Now, let's go back to the finite difference. And I'm going to, just to make things as simple as possible, because this is the hardest part, at least for me, I'm going to break this into just 5 wave function pieces, which is not a great idea, but we can do that. Okay, so 5 pieces. So I start at 0 and I end up at 4. That's 5. 1, 2, 3, 4, 5. Now, and there's my little bump, right? And I just pick some values. This wave function at this point right here, psi 0 and psi 4, are 0, right? They are set. Those are my boundary conditions. That's very important. So I don't need to change psi 0 or calculate psi 0 or psi 4. I only need to deal with these 3 in the middle. So that gives me 3 equations. I can write down the Schrödinger equation for each one of these 3 points. So here's that first equation. Instead of saying psi I put psi 1. And you'll notice that the one before it, psi I minus 1, is psi 0. And I changed the order a little bit. And then here's psi 1, and then psi 2, right? And then that's psi 1. So instead of saying I just put 1. And then I change it to 2. Here's I equals 2. That one has a psi 1, psi 2, psi 3, psi 2. And then I do it for psi 3, psi 2, 3, 4. Now, this could be a problem, right? But I'll show you. But the most important thing is that these are 3 linear equations in psi. I have these variables psi, and I have 3 linear equations. And again, psi 0 and psi 4 are constant. Really, they're 0. You could drop them out, but I left them in there. So if I have 3 linear equations, I can write this as the following matrix equation. And don't ask me to do this again, because I hate typing these in LaTeX. And I factored out this thing just to make it look better. But this is my ith term. And then I have these I plus 1 terms on the diagonals. And then everything else after that would be 0. Okay. And I multiply by a vector. I put psi 1, psi 2 as a vector. And that's going to be equal to E times a vector. And this is a really important problem, right? Because I have a matrix times a vector gives me a scalar times a vector. That's the eigenvalue problem. But let's just see how that works for a couple of these equations. So first of all, I wrote this as k v1, k v2, k, just because I didn't want to write all that stuff in there. So this is just that term. And this is not the way I would do it, but just the way it's easier to write that way. Okay, so let's just multiply this matrix out and see if it actually indeed works. Let's take this row times this column, and I get this equation, right? Because I get psi 1 times that, which is, should there be a 2? Oh yeah, there is a 2, because I factored out a 2 right there. So that gives me this term right here, right? Because the 2's cancel with this term. That gives me that term. And then the psi 2 times 1 gives me this term. I got that constant over there too. And then the psi 3 times 0, so it doesn't appear. And you'll notice that this term is 0, so it doesn't appear either. So it's all cool, right? Because that term's set. Now, if I do the next row, we're going to take this row times that column, and I get this one. Now, that one works, right? Because I have 1 times psi 1, this thing times psi 2, and that times psi 3. And then we could do the same thing for the last one. But this is our eigenvalue problem. All we need to do is to find the eigenvalues for this matrix, which involve taking the determinant and all that stuff. But it can be kind of complicated, even for a 3 by 3 matrix. But we want to do maybe a 99 by 99, and we can't do that. We're going to have to do that in Python. But I want to say one more thing. We're going to jump to Python. This is what we're solving, right? This is the Schrödinger equation. H psi equals E psi. And it's the same thing we see this eigenvalue problem in classical mechanics, right? I omega, no, it's I omega equals wait, what was it? Well, we see it. The eigenvalue problem for rotational matrices and stuff like that. Okay, let's jump to Python, and we're going to do this. And you know I'm a fan of like web v Python GlowScript, right? But in this case, I can't do that. I can't use web v Python because it doesn't have built-in support for matrices and stuff like that. So I'm using Jupyter notebooks. You can install this yourself. It's pretty easy. You could use Google Colab. That's an online version of it. They all do the same thing. So, but in normal Python, we have these cells that we're going to run. We can break it into cells. You could put it all in one cell, but I don't want to do that. And but we have to load some modules that tell us how to do things. So I'm going to load 2 modules. Import Numpy as NP. And some people will say NumPy, and that's probably correct. But it looks like Numpy, and I like to say that. And then I'm going to import, and Numpy has all your numerical functions in there. It has matricey stuff. It has square root, sines, and all that thing. So you need that square root. Import matplotlib.pyplot as PLT. This is a module that's used for plotting. I'm going to go ahead and run just these 2 things to make sure that everything's loaded. And you get the little star right there that says it's working. Now it's a 1, so it's done. Okay, now I need to make, I'm going to put my constants. So I have the square well. It has a width of A is 1. I'm going to have a mass of 1. And I'm going to use h bar equals 1. And you don't have to do that. You can switch back and forth between real and fake units. I'm just going to use these fake units right here because otherwise it's hard to like pick how big your divisions need to be and all that stuff. So it's just, we can worry about the units later. Now what I want to do is to break my numbers into even spaces. So let's just pick for now n equals 10. And I'm going to make a list of x values. I can do that with a thing called linspace. So x equals np.linspace. And I want to say go from 0 to a, and I want n pieces. Let's print out x, because that makes an array. And one of the greatest things about Numpy versus GlowScript is the array. The arrays are super powerful. Let me print that out. We'll run this, and you can see what I get. It goes from 0 to 1, and I do have 10 pieces, right? But if I want this to be 0.1, 0.2, 0.3, then since it fits it at 1, 0, and 1, then all the numbers in the middle, these are actually 9 pieces, right? Including the 1. So if I put this as n plus 1, and this is important for later, and I run it, I get what I would expect. It's not a huge deal, but this just looks a lot better. So if I want 10 spaces, right, I need 10 plus 1 points. And now we're all happy. Okay, now, I'm not going to print that anymore. I'll comment that out. I'm going to need my potential also as a list. So I'm going to say V0. Say V0 equals 10. And I'm going to do something else. I want to make V an array also. V equals, and I don't do things the best way. I do things the way that makes sense to me. So I'm going to print this, right? Because now I'm doing an operation with an array. If I take that array x and I multiply by 0, it multiplies every single element by 0 and returns an array of the same size. So this will give me something very useful. An array of zeros. But now v is the same size as x. Okay. So that's one way to do it. You could do linspace again, but I didn't do that. Okay. Now I want to let me see, what did I put for my code over here? This right here. Okay, so a over 4. So that's the width of my thing. So right over here, I want all these x values to still be 0, but if x is greater than a over 4, I want it to be v0. So that's what I need to do. And again, I'm going to do this my way. I'm not going to do it the best way. And I'm fine with that. So here's how I'm going to do that. I don't want to print that anymore. And I'm going to print it, and I'm going to change it. I'm going to print it again. So let's do this. For I in range length of x, this will go through all the values in x, which is the same length as v, and just call it I0, I1, I2, and so forth. And then I can say if x I is greater than 3 times a over 4, right? Because I said that was a fourth of an a. That is what I said, right? How did I forget this already? Yeah, a over 4. If that's true, then I'm going to change the value of v. So I'm going to say if that's true, if the x value, xi, is greater than 3/4 a, then vi is equal to v0. And if it's not, it's already 0, right? We already had that. So let's just print out v again and see if it worked. So it went through, it still has the same number, but these last 3 are 10. Right, because they were greater than 3/4. Now you could get into the question of what about at 3/4? What should it be? And the answer is no one cares, because if I have 99 points or 100 points or 101 points, then where that actual barrier is less of an issue. Okay, so now what we need to do, we have all our constants. We have x, we have v. And I need to make that matrix H, okay? So this is where we're going to have to use some of the power of Python. So let's just say this. Let me just say H. I'm going to write a matrix. H equals np.diag, np.ones, n minus 1. And I'm going to print that. And I'll tell you what, I didn't do it right. np.ones. Okay, so this made a matrix. So the np.diagonal makes a diagonal matrix. And I need to know what values to put in that diagonal, and it's going to be 1s. And I need to know how many 1s. And here's the very important part. Remember, the 2 endpoints are fixed, right? So I have size 0 and side last one are set. So that's 2 that I do not have. I need 2 fewer for my array. But I did n plus 1 elements. So 2 fewer would be n minus 1. So I have 11 pieces, and this is a 9 by 9 matrix. So we can make that. Okay. So now we want to go ahead and just make the diagonal, and then I'll make the off diagonal. So the diagonal is going to be equal to, I need to multiply it by h bar squared divided by m times dx squared. And now most of those values are 1, so it shouldn't really matter. But I didn't do it right. H bar squared. Oh, I missed some parentheses. No? I didn't find dx. Okay, I got to go up here and do dx. I'm sorry. So let's do dx. Dx is going to be equal to, you could do a over n, but I don't want to do that. I'm going to say dx is x1 minus x0. So x0 is the first x value, x1 is the second x value, and so that will give me dx. And if I run that, that's that. If I go back up here and run this, now I have that. Okay. So there's my list of values, and this dx is what makes that so large. Okay, so that's fine. Okay, now I'm going to try to construct, let's go back up here. This, right? So I'm trying to make this is my diagonal. So I got the h bar squared over m delta x squared, but then I have to add v1. So I need to add v1 in there too. So let's go up here and say plus np dot diag np dot ones n minus 1 times, I'll put it over here, times v. And it didn't work. Oh, they're different shapes. That's why. Remember, so my v is actually 11 elements long. So I want to cut off the first and the last one. So I can do that as 1 colon negative 1. And no, square bracket right there. There, I did it. And so now you'll notice here in my list, it goes 100, 100, 100, 100, 100. And then the last two are added 10 because that was my v0. So that did work. And any function I had for potential should work here. Okay, now I need to do the off diagonal. So let's do that. I'm going to put it down here. So let's do it as h equals h plus I want to do an off diagonal. What should my off diagonal be? Let's go back to this. So my off diagonals are this negative h bar squared over 2m delta x squared. Okay. So let's put that in here as, where'd my thing go? Here it is. Okay. H plus, it's going to be negative, I'll put it in parentheses, negative h bar squared divided by, now I have 2 times m times dx squared. And that's my constant out front. And then I'll say np dot diagonal, np dot ones. Now, this column, this diagonal right here, you'll notice it has 1, 2, 3, 4, 5, 6, 7, 8 elements. So that's n minus 2, right? N minus 2 is 8. And I have to add it, I have to add a comma 1 in my diagonal. So that means it's shifted off the diagonal by 1. So this should add values up here on that other off diagonal. Let's run it. And again, I'm making a lot of mistakes. Invalid syntax, NP, oh, it didn't do times. It's okay to make mistakes. That just shows you that it's live. Okay, so there's my off diagonal. Now I need to make the other off diagonal. It's going to be exactly the same thing. I'm just going to copy this. And you can put this all in one line. It doesn't really matter. The only thing I'm going to change is right here is minus 1. So I'm going to do the minus 1 off diagonal. So it's going to be the lower one down below. And there's my tri-diagonal matrix right there. And it's only a 9 by 9, but we're going to solve it anyway. And then once you have it for 9 by 9, you can make it 999 by 999. It doesn't really matter. Okay. Great. Now let's go ahead and solve this. There's a built-in function in Python that solves this eigenvalue problem. And it will return the eigenvalues, E, and the eigenvectors, psi. So I'm going to say E, psi. It's going to give me both of them. It's going to be np.linearalgebra, alg.eigh. And then I need to say what matrix am I solving for, and that's H. And it's going to, let's just print out all the E's just so you can see what they look like. So there's all my values of E's. Now, you'll notice that in the actual square well, you should get an infinite number of eigenvalues. They go up to infinity, right? If I have no bump, I know n can be anything. But this doesn't go all the way up because it's not a continuous wave function. Because we broke this into discrete points and we turned it into an eigenvalue matrix problem, we only get a certain number of solutions. And the same thing's true for psi. I'll just print out the whole psi, even though that's not a very good idea. Now, this does have a problem because this is psi 0. These are all the eigenvectors. Okay, these are all the values for the ones in the middle. Let's print out psi 0, the first one in that list, and that's it. And that's not the eigenvector, okay? It's not, because the way it prints it out, we actually want a column vector out of that matrix. So we have to transpose it to print this out. So we can do that with psi dot t, the 0th element, and that's the first eigenvector. So we did it. Okay, let's make a graph. Let's plot these things. So I have my eigenvalues. let's just plot. Should I do the labels? I'm not really great with plotting. Let's just not do the labels. You'd be fine with that. So I want to plot psi. Let's plot psi squared. When we didn't normalize it yet. So let's plot psi squared, and then we can normalize it. Let's just plot psi. So I'm going to say plt.plot, and then my x value is going to be x. But remember, my x has 2 extra pieces in it. So I don't want those 2 extra pieces. So I'm going to plot from x from 1 to -1. And then I'm going to plot psi.t 0. And there's my wave function. And you'll notice it looks a lot like the infinite square well, but it's shifted over a little bit because it has that bump. And that's what we'd expect. Let's do psi 2. And it's a little bumpy because we don't have that many data points. Let's do the same thing for x, and this will just be 1. That's the second, and then the third one. And there we go. Okay. Everything's great. Let's go ahead and increase the number of points from 9 to 99. So up here, I just need to change my n to 100. Now I need to rerun the cell. I do not want to print it out because it's really large. I do not want to print that out. It's really large. So I don't want to print anything. So I'm just going to run it. Now down here, again, I don't want to print it, but I need to rerun this cell. And just so you know, if you're not sure, you can always click Run, Shift, Enter, runs the cell too. I didn't say that. I'm not really an expert with Jupyter Notebooks, but I don't want to print that out. But I do need to remake the matrix right there. And now I need to remake all these plots. And shouldn't have printed that out. Let's cut that out. Okay, there we go. Now, you may notice that it's upside down. It's in negative. I think it doesn't matter. One, we're not plotting the endpoints because we didn't have wave functions for those. You could add those in there. I just don't want to deal with it. It doesn't matter. It doesn't matter if the vector is negative or positive. It's still an eigenvector, right? So, and we don't really care about the eigenvectors anyway. We care about the psi star psi. That's the probability density. So let's go ahead and normalize these functions. I'm going to do them right up here. How do you normalize a function? Well, what you need to do is you need to integrate over the whole space of psi star psi dx. And I can do that very easily with Python. So I'm going to call this constant a the integral. I'm going to call that a. And in Python, I can say np.sum, and I give it an array, and it'll just add up whatever's there. And for this array, I want psi.t 0 squared times dx, right? So psi star psi is psi squared, and then I have to multiply by dx. And that's my new little element piece, and when I add up all those pieces, that is an integral. And that will give me the area under the integral. Let's print that. And you see it's not 1, but we want it to be 1. So how can we make it be 1? I can make it be 1 by saying psi.t0 equals psi.t0 divided by np.square root of a, right? Because if I divide each psi by the square root of a, then when I go back and recalculate the area under the psi star psi, it'll be 1. And in fact, let's do that. Let's redo this and see what we get. So the first time we got 0.99, and then we got 1. And you'll notice that it doesn't look the same, so I need to normalize the other ones too. I don't know if the normalization is the same for all of them. I'm not sure, but it doesn't really matter. It's easy to do. And I'm doing this manually. You can do this better, but it doesn't really matter. So I don't want to print this stuff anymore. Let's just do the same thing. NP sum. I don't want to do. Oh, let's do that for psi 1. Let's do that. So that's normalizing psi 0. This is normalizing psi 1. And now I need to I integrate. And now I need to normalize it. So psi dot t1 equals psi dot t 1 divided by np dot square root of a. And then I'm going to copy this one more time, and let's do it for 3. The third one. And this is, oh wait. No, that's third. Yeah, okay, so this says 0. This is 0, 1. Okay, that's right. And then I'm going to plot the probability density by just squaring these. And there we go. Now, one of the things that, you'll notice that it is shifted over a little bit. This is a little bit higher, so it's not your infinite square well. But if you want to check, if you're always not sure if it's working or not, you can go back up here. I could just say V0 is 0 times 10. Rerun this, rerun this, rerun this, and I should get the infinite square well. And I actually know print E0. I know what the energy should be, and that is it. You can do that manually. You can check because we know the analytical solutions. Okay, so we did it. We did a non-trivial 1D square well using matrices stuff. And like I said, I forget this all the time. I don't use it and I forget it. I forget how to make these matrices right here. I always forget the diagonal thing. I forget this part. I forget how to plot. I forget how to normalize. I forget everything. So this is for you, but it's really for me, because I'm going to come back and I'm going to look at this in however many years next time I teach quantum mechanics 2, and I'm going to say, aha, I remember now. So there you go. Okay, so, but the really important thing is now that we have these wave functions, we can use this in other situations. We can do time evolution and stuff like that. It's going to be awesome. But I'm going to stop there. Hope that's useful. I'll talk to you later. The end. I'm leaving. Bye.